Welcome. Let us recall what we did in the last lecture. We are discussing about convergence of series. Now, we discussed about some of the tests which involves which will enable us to determine whether the series is convergent or not. So, namely all the series which consist of the non-negative terms, then we have basically three tests. One is the comparison test, which is extremely powerful, and if we have two series A n and B n, both of A n and B n, they are non-negative and B n is greater or equal to A n, or A n is lesser or equal to some constant times B n, then if B n converges, then A n is going to converge. Similarly, if A n diverges, then B n is going to diverge, summation of B n is going to diverge. And as a consequence, we can derive the root test as well as the ratio test, which we are familiar with. So, now let us talk about the complex series. Now, if we have A n, for each n, A n is a complex number. So, where A n is equal to x n plus I y n, where x n is the real part of A n and y n is the imaginary part of A n, then we will say that the series A n converges if and only if both the series x n and y n, summation over x n and summation over y n, this converges. Now, in this case, we will say that A n is series A n is absolutely convergent if summation over mod of A n is convergent. So, now mod of A n is a non-negative real number. If this converges, we say that the complex series summation of A n, this is absolutely convergent. So, easily one can see that if summation over mod of A n convergent, then summation A n is also convergent. However, the converse may not be true. So, all of us we are familiar with the alternating series. That is what the example I have taken. You take n equal to sum over n equal to 1 to infinity minus 1 to the power n over n. This is convergent, but not absolutely convergent, because if I take the modulus, then minus 1 to the power n is 1, and then we know that summation 1 over n is not a convergent series. Now, there is a test how to determine when an alternating series is going to be convergent or not. That is the so called Dedekind test, which says that you take A n and B n, the sequence of complex numbers, and let the partial sum of A n, that is bounded, and the absolute value of the difference of the two conjugative B n, this is convergent, and B n converges to 0 as n goes to infinity, then what we get is that summation over A n B n convergent. For example, like in the previous case, so now if we are taking the summation of this S n, if we take the series to be minus 1 to the power n by n, then this S n A n is equal to minus 1 to the power n and B n is equal to 1 by n. then S capital of n, this is equal to summation over n equal to 1 to n minus 1 to the power n. This, as you know, that depending on n is odd or even, you will get that this is definitely less or equal to 1 for all n, capital N, and that shows the first condition is satisfied. And in the second condition, 1 by n minus 1 by n plus 1, this is equal to 1 by n into n plus 1, which is a series of the form 1 over n square, and that is by the comparison test, this I can do it less or equal to 1 by n square, and this converges, and B n of course converges to 0, then A n B n convergent. Okay. So, now we will talk about some more convergence. Now, if we have got two series A n and B n, be two absolutely convergent series which converges to A and B respectively. Summation over A n means the partial sum of A n S n equal to summation over n from 1 to n A n, this converges to A. Similarly, the partial sum for the series B n converges to B. Now, what can we say about, then we know that the summation, then this series A n plus B n, this converges to A plus B. And now, what about the product? So, now to discuss that, let us define C n to be summation of k from 1 to n A k b of n minus k. Then in that case, this is the Cauchy product, and this series C n converges to A b. This is the pointwise multiplication of A and B. Okay. So, if one of the series either A n or B n, if that is absolutely convergent, then also we get the same result, that summation of C n, n from 1 to infinity, that will converge to A b. But if now it is natural to ask, suppose we have only the condition that summation of A n converges and summation over summation of B n converges, is it necessarily mean that this Cauchy product is going to converge to A b? In fact, the answer to this question is in negative. So, let us look at a very easy example of this series of two series which are convergent, but their Cauchy product may not converge. Now, for that, let us take A n to be minus 1 to the power n minus of 1 by square root of n, which is also equal to B n. Now, if I compute C n, then this is going to be now minus 1 to the power n minus 1 is a k minus of 1 into minus 1 to the power n minus k plus 1, n minus 1 minus k. So, now getting cancelled, we will get that it is minus 1 to the power n is going to come out of it, and what is left with 1 over square root of k and 1 over square root of n minus k. Now, if you take the modulus, then this mod of this is equal to 1. Therefore, this term goes away. Now, the remaining term, whatever inside this, or both of them are non-negative terms. 1 over square root of k is greater than 0 and 1 over n minus of k. Here there is I can take this to be minus of 1. So, this is also greater or equal to n 1 over square root of k is greater or equal to 1 over square root of n. because k is lesser or equal to n minus of 1, and 1 over square root of n minus of k is greater or equal to 1 over square root of n. Therefore, and then the sum, if I take it all these terms from the sum, I have n minus 1 term. So, this is going to be greater or equal to 1 for n greater or equal to 2, let us say. So, however, we know that if the summation C n converges, then this will imply that C n, the sequence C n goes to 0, but here we have got the mod of C n is greater or equal to 1, therefore, it can never go to 0. Therefore, this series does not converge. So, Cauchy product, one of the series, either A n or B n, at least one of the series has to be absolutely convergent to get the Cauchy product to converge. Now, another familiar series which we deal with is the power series. Let A n be a sequence of real numbers. Then the series of the form A n x to the power n is called a power series. Now, if I am taking x to be the whatever the x is, this is suppose a particular x, then A n x to the power n is called the power series. If whenever the series converges, then it makes sense. Now, if there exists a capital N such that A n's are 0 after capital N, then this is called a polynomial. So, in a sense the power series is nothing but the polynomial plus 3 dots. So, now what we know is that if a power series converges for some x naught, then the power series will converge for all those x lying on the left of x naught. Mod of x naught, mod of x is less than mod of x naught, then the power series converges in this region. Okay. And similarly, if the power series diverges at some x naught, then any point lying outside the x naught and minus x naught to x naught, then those series for those x the power series is going to diverge. So, now the question is what can we say that what is the region in which the power series is going to converge. So, natural thought process will tell that okay. So, what we will do is that we will check all such x naught for which a power series converges, then we will stretch it. That means, we will take the supremum of all the x naught for which power series converges, then in that region suppose it converges here x naught, then I will go further and up to this point where there is a break, that from this point the power series diverges, but rest of the thing converges, then in this region the power series is going to converge. So, that idea, so how to find what will be the region for the convergence of a power series, we have concept of radius of convergence. Now, we look at r small r to be limit n goes to infinity mod a n to the power 1 by n. It may or may not exist. If it exists, then we say that the radius of convergence is 1 over this small r. That is what is the radius of convergence, and then the series converges absolutely for mod x less than r. So, which is essentially showing that it is going to be dominated by a geometric series, and we know how to compute determine the convergence of the geometric series. Now, consider the series x to the power n, n to into 2 to the power n. Now, then if we take 1 by n to the power 2 over n. So, this is my little r. So, this is going to, the limit will exist and be 1 by 2. Therefore, this is nothing but r. Therefore, capital R is going to be 2. Now, the radius of convergence is going to be 2. That means, any x such that mod x is less than 2, the power series is converge. But now, what happened to mod x is equal to 2? There we can see that it, we have got 2 point plus 2 and minus 2. Now, if x is equal to 2, then the series, if x is equal to 2, then 2 to the power n, 2 to the power n get cancelled, we get n, then now that is a divergent series. Now, if x is equal to minus of 2, negative 2, then if we put that, then the series become minus 1 to the power n by n, and that we have seen that the series converges. So, in the radius of convergence, if the radius of convergence is r, then mod x less than r, it converges, mod x greater than r, it diverges, mod x is equal to r, we can't say, at some it may converge or may not converge. That is the essence of the story. We let us recall that a convergence of the sequence of functions. So, we have a sequence of functions defined on an interval I, real valued function, and we say that f n converges to f for some f pointwise if f n x converges to f of x as n goes to infinity for all x in R. That means what? Given an epsilon positive, there exists a n sub naught. Now, this n sub naught will depend on epsilon and on x. For each x, there exists a n 0 x we can put for our convenience, such that mod of f n of x minus f of x, this is less than epsilon for all n greater or equal to this n 0 of x. Now, if I can find for a given epsilon, any epsilon, if I can find n 0 x, that is for every x. You see, here the n 0 x can vary if we vary your x, but what we need for a fixed x, we must get an n 0 n sub 0 for which this happens. Now, one can see that suppose what kind of property of the functions is being preserved with this convergence. The most natural thing to ask is that if we are dealing with a sequence of continuous function, then will it, and it converges to another function f of x, then is it true that f is going to be a continuous function? And that is not true, that is what we know, and the example you can easily see that if you take f n of x is equal to x to the power n, where x you take in 0 and 1, then this converges to, here is the function, and this converges to 0 as n goes, if x is not equal to 1, because x is, then in that case x is less than 1, therefore, x to the power n will converge to 0. Now, if x is 1, then this is going to be f of x is going to be 1, because all these f n x, f n of this is true for all n. Therefore, now f n at 1 is a constant sequence 1 and which will converge to 1. So, now this the limiting function what we are going to get is up to 1 this is 0 and at 1 this is 1, and certainly this is not a continuous function on closed interval 0 1. So, now what extra condition we give in the convergence, which is going to give us that the limiting function will also be a continuous function if we are starting off with a sequence of continuous function. So, now what is uniform convergence? Uniform convergence is that for given epsilon, there we are finding a cap n sub 0 which was depending on x for each fixed x, but here we will get one n, that is uniformly for all x belongs to I. If we manage to get such a n, then we can say that f n x converges to f of x uniformly. And this uniform convergence, and in other words we can say that the supremum for a given epsilon, supremum over x belongs to I, f n x minus f of x mod is less than epsilon for all n greater or equal to n. This and this preserves the continuity in if f n is a sequence of continuous function on I and f n converges to f uniformly, then f is going to be continuous on I. Okay. So, now this is a very brief recall of infinite series and convergence of sequence of functions. Now, we would like to recall some basics of Riemann integration. So, Riemann integration is a method which tells us to find the area under a curve f. So, now we want to find the area of this region. How to calculate this area under this region under this curve, and this is what is the prescription was given by German mathematician Riemann, Bernhard Riemann, who developed in the mid 19th century, and this is the picture of Riemann. Okay. So, now I have a function f from closed interval a b to r, and we are assuming that f is bounded. That means, there exists a m greater than 0 such that mod of f of x is lesser equal to m for all x belongs to closed interval a b. So, how to do this? So, as you recall that what we do is that we divide this the entire interval a b into a b, then what we define, this is a is x 1, x 2, x 3, x 4, whatever it is x n, and then this is some point, we keep on dividing it, and this is nothing but x n, and this point is x n minus of 1. So, we are just partitioning it, where you see the length between these two can vary, conjugative x I and x I plus 1 can vary. So, we are this is called a partition of a b. So, now, the Riemann sum with a given partition is that, so you have a function f which is defined on, this is A, this is B, and you have some partition x 3, let us say here, this is x I, this is x I plus 1, and this is x n. So, now you choose any point C I here. Now, at this point you have, you take this rectangle, and similarly you choose any point over here, consider all these rectangles, you keep on doing it. So, now you get the Riemann sum, which is essentially the rectangle here, it is nothing but delta of x I, and this is the height of the rectangle. I am choosing here a non-negative function. So, for my picture, so what we have got is that that is the Riemann sum f c I delta of x I, and to define the Riemann integration, we define, remember that this is the partition P, so now this norm of P I am going to define as the maximum of all this difference. So, this is my x 2, this is my x 3, like this. So, maximum of the length of the interval, and now we say that f is Riemann integrable on A B if the limit of the Riemann sum corresponding to P that goes to, that exists, and then we denote the Riemann integration to be A to B f of x is the limit of norm P goes to 0 R of f P. Thank you.